Talk about long-acting antiretroviral therapy, we are talking about the absence of rebound with intermittent therapy. So instead of giving medicines every day, you might be able to take them every month or every 3 months. And obviously that's in relation with sustained remission, is when you do something and you stop therapy and then you don't rebound when you stop antiretroviral therapy. And you don't have to take the medicines, but if you look for the virus, you can still find the virus in the DNA of the CD4 cells. And then cure, which is the holy grail of HIV research, is to get to sterilizing cures. You stop therapy, but you have eliminated the HIV virus from the reservoir, the CD4 memory cells. But all of this is a continuum, and we probably will reach this probably this year. We will have intermittent therapy available and approved this year. This is going to take a little bit longer. I don't know if we will ever get to this in a practical way for most people living with HIV. This is my outline, and we are talking mainly about the future. I'm going to talk a little bit about antiretrovirals and data that was presented in Mexico. Cabotegravir and rilpivirine will be approved, if everything goes according to plan, probably on Christmas, almost on Christmas Eve. I think the day that the FDA is supposed to render a decision is December 28th. Pro 140 is going to be approved, is an antibody, and I'm not going to present too much data about it because we have talked about this before. And Islatravir is a new drug that Merck is developing that probably will be approved next year or probably the following year. We'll talk a little bit about sustained remission, and I will talk about the prospects for a sterilizing cure. So these are the studies that were presented at the IAS last month. One is a combination of cabotegravir and rilpivirine for maintenance. There were 2 studies, the ATLAS and the FLAIR. Very similar design, people that were suppressed. Both of them were switch studies. They were randomized to receive cabotegravir orally because you don't want to give a medication that has a very long half-life if you don't know if the patient is allergic or not. So they had a loading phase with rilpivirine and cabotegravir for 1 month, and then they received intramuscular injections with cabotegravir and rilpivirine every month, and they presented data up to 58 weeks. Or they continue the oral regimen. Similar study, and you have seen these graphics, which is the snapshot analysis that the FDA likes to present. 90% suppression, more than 90% suppression at 1 year, massive study, around 600 people, very little virological failure, people that don't make it to the 48 because they are lost to follow-up or there is not within window. And is within the interval of equivalence, so really continuing oral antibiotic therapy or getting injections intramuscular once a month is the same, is non-inferior. The FLAIR study is more of an induction, so people were naive when they went into the FLAIR. They get abacavir 3TC and dolutegravir. This is the VIV single tablet regimen, Triomec, and then they get randomized after being undetectable. After 20 weeks of this regimen, if they are undetectable, they get randomized to the same intervention, and the results are very similar. 95% of people maintain suppression, very little virological failure, and we will talk a little bit about this virological failure, complete equivalence. In the meeting, one of the big questions is, do people that are taking 1 pill once a day want to do this injection? And when they ask people in both trials, they prefer the long-acting therapy, 86%, and only 2% of the people prefer the oral therapy. In the other trial was very similar. You have to remember that these people volunteered to participate in this study because they wanted to get the intramuscular injection, so this is a little bit biased. I don't know what's going to happen in real practice when we start doing this type of treatments, intermittent therapy, for people living with HIV. During the meeting, they presented an updated version of the study. They put them together, and this is, it becomes more than 1,000 people study. And again, the results were very similar, around 95% suppression, and probably should have removed this study. There was not a lot of resistance, except Some people, when they fail the intervention, they have virological evidence of integrase resistance mutations. And all of them, almost all of the people that they had virological failure came from Russia, and almost all of them had clade A1 virus. And it was around 30% of the people that have this particular clade that is common in Russia that failed this regimen. So I think we still don't understand why this happened in this particular group, but if I had a patient that had a clade A1, I would probably not offer him or her this strategy as a maintenance strategy. This is something to keep in mind if you have a patient that has a clade A1. If you had a baseline genotype, you can look at the clade because it's usually in the upper part of your baseline genotype. So what have we learned from these studies? That in people with viral suppression and no history of NNRTI or integrase resistance, you can maintain suppression with cabotegravir rilpivirine every 4 weeks as an intramuscular injection. There were not a lot of serious injection site reactions. There is a small risk of drug resistance, particularly in clade A1. And this drug, based on these studies, I think they will be approved. The FDA will approve both of them in December of this year. The question is, how do they fit in our treatment paradigms? How are we going to be using these drugs in clinic? What proportion of people receive treatment will want this treatment? And it depends. If you ask physicians, they say, why on earth, if you're taking one pill once a day, would you want to get an injection once a month? If you ask patients, they tend to like it more, the idea of not having to take pills every day and not being reminded that they have HIV every day. So I don't know how many people will want this. How do you choose the right candidates? Because we would like to be able to use these drugs in people that are not very adherent to antiretroviral therapy, but that's exactly the population that you don't want to use these drugs. You want to use these drugs, at least at the beginning, in people that have been suppressed for a long time, and you know they are going to show up every month. Because if you don't show up at the end of the month, then you have a problem. You have a decreased level of an antiretroviral, and the virus is going to rebound, and then you're going to develop resistance. How do you implement this in practice? That's a very big question that I don't know how we're going to do. If 1 in every 6 people want this treatment, 15%, which is the number that had been circulated, in my clinic, which is, we follow around 1,000 people with HIV, 150 people will want this, and that means that every day there will be 9 or 10 people that will have to come to get the injection every day. And we don't have nurses to do this. We don't have a pharmacist that you can prepare the injection. So the logistics of it is going to be complicated. And how long people will want to be on this when they have to park every day in my hospital, which is completely insane. So after 2 months, I think everybody will say, I want the pill, and forget about this. How do we pay for it? All of this infrastructure that is not in our clinics right now, how are we going to pay for it? Because it's not going to be reimbursed. And the interesting question is, how are we going to use these drugs in people that have problems with adherence? We're looking at these questions in a study, and you can ask Dr. Santana, because I think you guys are enrolling in this study, about using cabotegravir and rilpivirine in people with issues with adherence in the past. And I think that's the population that this drug is really interesting. That study is now open. Merck has a new drug, which is a long-acting nucleoside reverse transcriptase translocation inhibitor, is how they call it. This is Islatravir. We found out in Mexico the name. This is the name now, Islatravir. This name is impossible to remember, MK85901. And basically it's a nucleoside analog, but because of the shape of the molecule, it prevents translocation. So one of the mechanisms of resistance to the nucleosides is to remove the nucleoside after being incorporated, and because of the shape, this is much more difficult to do, and that's why Merck claims that it's a new, not a class, but it's a new group in the nucleoside analog class. This drug is incredibly long half-life. So in this study, it was given to healthy volunteers, and they look at the concentration, 3 different doses over time. And here is not hours. This is not hours, it's days. So people are maintaining concentrations, particularly high dose, for days in the cells, in this, and in the plasma, for more than a month after one single oral dose. In Mexico, they presented this study that look at, this is a dose-finding study. They look at 3 different doses of this Islatravir and compare them to the dolutegravir 3TC and doravirine for 24 weeks, and then everybody roll over in the same dose for another 24 weeks if they were undetectable at week 20. And then they presented data on this time point, and they have to select a dose for the Q-day regimen, and this is the data that they presented. So again, suppressions around 85% to 90%. It was a little bit disappointed, at least for me, but you have to look at the numbers. One person that has a detectable viral load of 52 flips you and decrease this number by 3 or 4%. So it seems that the combination with doravirine, this is dual therapy, is very effective. And there was a little bit more of virological failure, surprisingly, on the high dose of the Islatravir, which doesn't make a lot of sense. They presented data at week 48. After this, the people that were not undetectable at week 24 were excluded from this analysis. And you can see numbers around 90%, which is what you expect in this type of a study. This is a typical dose-finding study. I would not put a lot of money on this effectiveness. I think they need to find out the right dose. How are we going to dose this drug? And then we will see what is its place in HIV treatment. The most interesting study that was presented in Mexico was this, because this drug is very attractive for PrEP, and Merck has a lot of experience dosing with implants for pregnancy, to anti-contraception. And they deliver this drug in an implant, and it can be given sub-Q, and they give it to healthy volunteers. With this implant, they think they can give enough drug to maintain levels for PrEP for more than a year. And that is, I think it will be a field changer for prevention and maybe even for care, for treatment. They presented data in healthy volunteers for 16 weeks of follow-up, and they maintain levels with a 62 milligram implant for more than 12 weeks, maintain levels that is considered therapeutic levels. And if it works for prevention, if you have the right 2-drug combination, you might be able to do this for treatment too. This is a drug that is in development by Gilead. It's a capsid inhibitor. It's given sub-Q, and here you can look at weeks. This is not even days. This is just weeks of, and after a single injection, you get levels above the IC95 for 12 weeks. You can imagine combining this with the other drug in an implant, and you might have enough to completely suppress virus for a long time. And that's where the long-acting crosses to sustained remission. So they presented data in healthy volunteers, and they are going to start a study in HIV positive, a phase 1B in HIV positive, and they will give this as monotherapy for a couple of weeks, and then people will receive triple therapy after that, just to looking at the pharmacokinetics of these drugs over time. Another drug in the long-acting category, a group of drugs that is getting a lot of publicity, is these broadly neutralizing antibodies. So broadly neutralizing antibodies, these are antibodies that everybody with HIV makes antibodies against the virus. Some people make antibodies that neutralize many of the different clades of the virus, and they are called broadly neutralizing. Those antibodies don't work for the individual, but neutralize other clades of other individuals. And there has been a plethora of these antibodies being developed that bind to the GP120 of the virus in multiple different sites, and some of them are starting to be tested in vivo. The interesting thing is that because this GP120 is also expressed in the cells when the virus is coming out of the cell, these antibodies bind to the cell and might eliminate part of the reservoir. And that's why people have a particular interest of these compounds in cure strategies. They can be modified. You can change the antibody, the tail of the antibody, and make them very long-lived. So this is the substitution LS in the tail of the antibody, VRC01 LS is a substitution in the tail of the antibody. It makes not clear by the complement system, and these antibodies can stay in the circulation above levels of micrograms per ml for 16 weeks, and in some of them. So if you find the right combination of these antibodies with long-acting antiretroviral therapy or combination of antibodies, you might be able to maintain suppression with combination of these products without taking antiretroviral therapy. We presented data, Jorge was an author of this abstract, about the activity, the antiviral activity of VRC07 52-3LS, is a CD4 binding antibody, and you can see this drug alone have a 2-log decrease in viral loads in patients that have not been on antiretroviral therapy, and is a long-lasting activity for 14 days in these 2 different antibodies. The interesting thing about BRINAbs is that they are starting to be used in combination. This is a study that Pilar Mendoza from the Rockefeller in New York, they wrote it in September last year in Nature. They gave a combination of 2 of these antibodies, 3BNC117 and 101074, to people that were fully suppressed with HIV. They gave 3 doses of the antibody and they stopped therapy. And the antibodies, when they are present in the circulation, you can see the blue and the red here, they maintain viral suppression in black. And when they disappear of the circulation, the virus rebounds in almost everybody. But there are 2 individuals in which the virus doesn't rebound after the antibody disappears. So these people were treated and with these 2 antibodies, therapy was stopped. And then when the antibodies disappear from the circulation, the virus didn't rebound. This is what people are talking about, a potential functional cure. The virus is still present in the reservoir, but for mechanisms that still we don't understand why, the virus doesn't rebound. This is a very important paper. This is only 2 people. One of them have rebounded after 30 weeks, but the other is still fully suppressed in the absence of medication and in the absence of everything. And the theory is that what happens is the antibody binds to the virus and sort of creates a new antigen, and there is an immunological response against this new antigen and blocks the virus from coming out from the reservoir. That has to be proven. It also improvements in the cellular immunity, but this is the way we are going to start looking at these drugs. The other thing important that has happened this year is that we have had a second cure of HIV. It's called the London patient. It was presented in CROI this year, and it's very similar to the Berlin patient. In fact, probably we have a third cure of HIV. It's called the Dusseldorf patient. So these patients are similar in some way. Both had an allogenic bone marrow transplant. Both receive a bone marrow transplant from somebody that doesn't have the co-receptor for HIV, so CCR5 delta 32 homozygous donor of the bone marrow transplant. And in both cases, when therapy was stopped, in one case almost immediately after the bone marrow transplant, and in the second case they waited for 16 months before they stopping therapy, in both cases the viral load never rebounded. So this is nice to have an N of 2 instead of an N of 1. And as Paula Cano likes to say, if you want to prove that a dog can talk, you only need one dog that talks. So if you want to prove that HIV can be cured, you only need one person that has been cured of HIV. Now we have 2, maybe 3. So these studies have shown that this is a way to cure HIV, and you can do it. Although this might be a cure, it's definitely not the cure, because people have been trying this for a long time, and it took 10 years to replicate the Berlin patient. 10 years to replicate the Berlin patient. Now we might be getting better at replicating the Berlin patient, but it still is not the solution for the 37 million people living with HIV. An allogeneic bone marrow transplant, you don't desire that to your worst enemy. Okay? So the Berlin patient doesn't have HIV, but has a lot of problems, including chronic graft versus host disease, and has to take medications all the time. So it is a cure. It proves that we can cure HIV. It is not the cure for everybody. I'm going to briefly go over what we are doing for gene therapy to treat HIV. So the traditional gene therapy approaches to cure HIV is, what we do is we take cells from patients with HIV, your cell of choice. You take CD4 or CD34, this is stem cells. This is regular CD4, which is what we tend to do at Penn. And then you do a modification of the cells to make them resistant to HIV. So most of the activity has been to modify the cells to prevent the entry of the virus, because nature has done the experiment. So you don't have the co-receptor, you don't die and for HIV, and those cells become resistant to HIV. But people have tried to modify multiple different aspects of the HIV viral cycle, but this is where most of the activity has done. And what you do is you infuse those cells back into the patient, and then you let the HIV virus do the selection. So you have cells that are resistant to HIV, cells that are in orange that are not resistant to HIV. When the HIV is replicating, the cells that are resistant to HIV proliferate, and you hope that over time they will take over the immune system and the virus will not rebound. We presented this paper a few years ago in the New England Journal, and we modified the CD4 cells by using zinc fingers to remove the CCR5. And we proved that those cells have a survival advantage in the presence of HIV. We didn't cure anybody. We presented this year at CROI, in collaboration with the BID, combining that approach with cyclophosphamide to make more space for the genetically modified cells, and using a machine to deliver them, to deliver the zinc finger nuclease using RNA. And these are complicated studies that there were 3 cohorts: people that got just the zinc finger nuclease treatment, people that got 1 gram of cyclophosphamide as a conditioning regimen, and 1.5 grams per kilo in the second cohort, and then we stopped therapy. And what we showed in CROI is that this is the curves of the rebound. So the people that have no rebound after 2 weeks of treatment, we saw a shift to the right. So this is similar to what you see when you give a monoclonal antibody. One monoclonal antibody, there is a delay on the viral rebound. We show that when we give cells genetically modified, there is a delay on the viral rebound. Not to jump up and down, because this is, if you rebound instead of 2 weeks at 4 weeks, really you have not made a huge difference. But it tells you that you have been able to modify the immune system to make it a little bit resistant to HIV, and maybe in the future this will be a therapy that will be used in combination. The other thing, based on these 2 patients that I have talked with you about before, that they got the antibodies and they didn't rebound when the antibody became became undetectable, people are trying to genetically engineer cells to make the antibodies. Instead of having to give it to people IV, you can do gene therapy to make them, the people make the antibodies and prevent the viral rebound. It will be a one-time treatment. And people are trying to do this in gene therapy using all the new broadly neutralizing antibodies that have become available in the market. And we will see trials doing this. You can deliver this by modifying the cells, but you can also deliver using a vector. You can inject a virus that expresses those antibodies, or using even DNA. And that is, I think, a new gene therapy approach that is going to be used in the future. The other thing that people are doing is try to engineer the kill. So we know that CD8 T cells eliminate HIV virally infected cells. So you can engineer CD8 cells to recognize HIV infected cells, put them back into the person. I know it sounds like science fiction, and probably is, but and then they will target HIV infected cells. This has become incredibly powerful way to treat leukemias. There is a drug that has been approved called CD19. that basically they put out a CD20 antibody and make CD8s fighting leukemic cells. And is incredibly powerful to eliminate the leukemic cells in people that didn't have any hope of cure before. You can engineer this to target cells HIV infected. It has complications, but the first trials are going to start literally next month to giving CAR T cells to people with HIV to see if you can eliminate the reservoir. And the last approach that became the news on CNN, and this is my last slide, was using what is called a combination of CRISPR-Cas9. If you are following this literature, CRISPR-Cas9 is like zinc finger nuclease, basically targets a particular sequence of DNA, and you can make it, modify it so it can be eliminated from the genome. So basically it's a way to try to eliminate HIV that is part of the reservoir, targeting cells that carry the HIV proviral DNA to eliminate it from the body. The experiment was done in mice. And they combined that CRISPR-Cas9 with laser antiretroviral therapy. Long-acting is a way to modify typical antiretroviral therapy to make them very long-acting. And what they did in this experiment that made the news is they treated mice, humanized mice, with no treatment, CRISPR-Cas9 alone, laser antiretroviral therapy, and then some group of mice were treated with the combination of CRISPR-Cas9 and laser antiretroviral therapy. All of the mice, when you stop therapy, the virus rebounded. But the mice that were treated with both, half of them, a third of them, when they transferred the human cells to another mice, the virus didn't rebound. And the authors claim that they cure HIV. They were not able to isolate. When they look at the HIV virus in the cells, they were not able to see the virus, and they claim they have cured HIV. That's why it created a lot of excitement in the research community and among the patients. So this has to be proven. Studies have to, you can cure HIV in mouse. It's much more complicated to do in primates than much more complicated to do it in humans, as we all know. And so gene therapy and HIV cure, the N2 support our efforts on finding a cure for HIV. Advances in immune therapy, cell, gene engineering, and delivery system will make these approaches easier to implement in the future. And gene therapy might be a part of combination approach to the HIV cure. And that's all I have to say. Thank you.